Okay. This is our lab. Actually, in this year we changed many things, and the first thing that you can tell is that we use another software to present instead of PowerPoint presentation. Okay. Yeah, it's about MRL extended ETDP, and actually I want to explain some major changes in AI, electronic, and mechanic. So let's start with AI. This part is our AI, subsection of the team, and let's see what happened this year in our AI. Okay, also I'm just so familiar to this software. Okay, we change our architecture, software architecture. We use a new game planner. I will explain to you. And we really needed to play a dynamic game, and also we use a strategy manager, and we will see what happened in. We have a role assigner. It's based on the CM Dragon also. Actually, our game, a strategy planner gives us opportunity to play as a dynamic game, and we in each strategy we use predefined rules and just select which rule and where we should use. As you know, dynamic role assignment is so complicated compared to the static one. Okay. What we have in a strategy manager. In a strategy manager, suppose we have different strategies, as also Parsian team said something about it. We have three kind of selection between the strategies. One of them is a random selection. It's just based on the probability. The second one is a highest score based on the way the field is occupied by the robots. We select the best strategy with probability. And the last one is the weighted random selection. We can select which strategy is more effective in each game. Suppose when we play with the first team A, we know them and we use some special strategies. And when we want to play with team B, we use another one. Okay, it's a sample of a strategy. It's a sweep, and left and right red robots are going to change their positions, and the robot number 6 give pass to that position, and we hope that we score a goal. Okay. Let's talk about game planner. It's, I think it's one of our main contribution in this year. Game planner is so important for us because we do all the things based on the data game planner provided us. What's this data? One of them is which player of the opponents are most important, are most dangerous. I will explain to you how we did it. Actually, we always think about really, really good teams like Scuba, like Immortals, and other teams to have a good game planner. Okay. And the thing in the game planner is think that we have really, really complex computations. And we make them parallel, and so we can use GPU programming as also like Parsian. We use CUDA to handle the parallel computation. So this is the part that we want to find the most important attacker of the opponent. How we do it? We assign a number from 0 to 1 to each robot of the opponent. Always the goalkeeper is 0. It's obvious. But it's really important to find the first, second, and third, especially when we have 6 robots. because some teams, attack with even with four robots. Some of them are fake. We should skip them and find the, the goal, the target for the pass. How we can do it? We put the ball on different position in the field, and heuristically, maybe based on your team, based on Scuba, or any team that we want to play with it, we guess which robots, which positions are really important for us. And then you can see the scores for any position with the blue circles. Then we fitted a Gaussian function to the scores. This is for one position of the ball. Then we changed the ball position and again we fit another Gaussian to all data. This by now this is for a static ball. The ball is stopped somewhere. Now we change it to the ball that goes around and robots. How we can do it? We do it with the same Gaussian multiplied by the velocity of the robot. In which direction, with which velocity, we change the score. Roughly speaking, when the robot goes have a velocity to this point, we actually doesn't compute the score of this position. Actually, we compute the score of that position. If this position is so important, we know that these robots are going to be the first attacker. Okay, this was a part of game planner. Another one is the regioning. Regioning actually is for us. We want to find the best position to give the robot a pass. This positioning is also like the Parsean is based on some lights algorithm. We put a light, a point light in any grid points and find the free space to the goal. And you can see in slide A, also our game planner can decide when one of the opponent robots are close to our robot. If we move our robot to this point, probably the opponent come with us, and this gives us more space to kick the goal. Okay, and we have some other thing. I don't really want to explain all of it. It's a debugging, online debugging. We can tune PID, PID for wheels from the software, and then send it by wireless to the ARM. This is done by some kind of interface between AI and microprocessor we have used. And this is the chart that we do it in our AI. These are velocities and other tabs. Okay, let's go to the our visualizer. In our visualizer, we can change many things. Not actually in the game, in timeout. It's so fast. We can put ticks anywhere we want. We can select a strategy, which strategy are better, or how we want to defend, and all the things that we can change during the match. Okay, let's go to electronic. This one is our new board. Actually, we tested, but we were a little bit conservative, and in this match, we used our old boards. That was modular. This one is one board, but it's working. And the main changes are, this is the structure. We use ARM7 and FPGA. We do the real-time things by FPGA and some other things by ARM, like setting the kick power or something like this. And the other things. Last year, we use opto isolated to isolate the logic part of the electronic and the power part of the electronic. This was some drawbacks, like maximum we are limited to maximum working frequency. Some kind of delay, and the optos takes really large space in board. We skip them by using a new grounding classification, and so by this modification we can go more than 1 megahertz in frequency, and the loss in power and switching decreases. Okay, this was our new motor driver. Thanks Tiger team to introduce us bootstrap drivers. We changed because we want to use N-channel switches. As you know, P-channels have many difficulties. And N-channels, for N-channels we use a bootstrap driver to do this. Okay, we have a wireless communication. We changed some modification. We have some modification in wireless communication. I skip this. These are our new wireless board. And okay, solenoid optimization. This one is the other part of our this year work. As you know, the speed of the kick speed is decreased to 8 meters. We think that why we should use the same kicker system to the last kicker system has ability to kick as 12 meter per second, but we are restricted to 8 meter this year, so we decide to do some optimization. This optimization, the objective function is the weight of the kicker system, all of it. The coil, the plunger, capacitors, all the things. But there are many restrictions in the space. In the resistance of the coil, because the wire cannot accept any current we need. So we do the optimization with more than 7 variable and more than 10 constraints. Mechanical constraint, electrical constraints, and the most important one is the speed of the ball. So yeah, for example, I just want to explain one thing. If we have, if we increase the weight of the plunger, this changed many things, not just one thing. So optimization is it's not a kind of convex optimization. There are many local minima, so we use genetic algorithms to find the best combination of the. As a result, I can say we can kick the ball as previous, but with 150 grams less kicker system. And as you know, this decreasing in weight gives us opportunity to go so faster, just acceleration, but it's so important. Okay, the result of this optimization will be published as a paper, maybe conference or journal. So until now, anyone if wants, all the variables and the procedure, just send an email to me. I will explain to him or her. And as a mechanical design, we changed something. The most important one, we replaced the ring by the pin. And I know many teams did it before, and now we really saw what happened with this pin, the free wheel. It gives us opportunity to go really online, vertical or straight motions. We change our stance before we don't have this fillet, and without this, in any collision, we were in danger to, lose the stance. And as you know, we measure about 5 microns in, going far from the real position is really, really bad, and the robots can't go really fast on the, straight line. So we use this part, we added this part to our stance and analyze it by mechanical software. I'm not so familiar with this to find the tensions and remodify the design. Okay, our changes are not changed this year, and our dribbling system. In this year dribbling system, we changed the system in 2 parts. We divided it in 2 parts. A fixed part here that we put sensors on it, so when the ball is in the dribbler or is not, the place of the sensor with the chip key does not change, and this gives us opportunity to have more precise chip keys. And the damping part that, like any other teams, give us to, for catching the ball. This one is the fixed part, and this one is the damping part of the robots. Okay, another thing is the color. It seems it's not so important, but it's so important. Last year we used fiber carbon, and after that we found that it has really bad effect on the wireless. And some guy in our country tell us, okay, when they want to build, AUVs that don't see by the radars, they use carbon fiber. So we said, okay, we should change it, and this year we use polyethylene, and by the CNC machine we do this, and we decrease the weight of color until 50 grams, and we don't use any screw on it, so we can put it and put it on the robot, and again take it in really fast manner, and also solve the wireless problem. So thank you everybody, and thank you also Crazy to provide this presentation tool. I'm here for any questions.
Questions for MRL?
Yes. Actually, you said you take some points and evaluate them for your opponents, and see if those points are the possible points for them to beat or to pass, right? And then right after that, your robots are going to cover those places, am I right?
Covering is different. Sometimes, sometimes we go as a marker so close to that robot. Sometimes just we cover its view to the goal from distance. It depends on the place of the robots.
So if you calculate in 1 second, and then it takes a little while for a robot to reach that place and cover the areas, right? And then the situation changes. Maybe the other team's decision also changes. You say this place is the best place for an attacker to be. So I'm going to cover that area. You send the robot there, the situation completely changes, and then maybe the last place of your own robot, the one that went for covering, becomes the better place for the other, for the attacker, for the opponent to be and to keep towards the goal. So how do you?
Yeah, actually, scoring. We just use the scoring when we are in defense position, when we are defender. We don't use it for, because when you are defender, you are a follower. But when you attack, you are a leader. when you attack,
Sure, but I'm not talking about your attack. I mean, your defenders go cover areas that they thought were going to be dangerous areas. And then the situation changes.
sorry, not dangerous area, dangerous robot.
Uh-huh.
Maybe this is the point that you are looking for. Yeah, but always there are, it's a dynamic environment. This year, I think the JU team maybe totally destroyed our scoring because your robots after the kickoff or free kick changed so much in the field. So sometimes in our friendly match, I saw the log, and our robots a little bit confused between scoring, and so this is the way that other teams can confuse us.
There was also another question. You said you assigned some, as you call them, scores, some weights to the opponents, right? I mean, the goalie is always 0, obviously you said. And then how do you set the values initially? How do you decide which should be right now should be something, and then the game decides whether or not that was the right value or should it change? I mean, what are the initial values?
Initially you mean offline scoring.
Yes.
We just do it based on the most strategies team usually done. For example, there is now it's a common strategies when the ball is in our field, in the opponent field. The strategy is that they put a robot close to our stop cover robot, and then low chip kick, and this robot comes, and so this area is so important and really have high score. Another area is the area on that side of the field, because many teams do do a rotation, give a pass, and kick the
You
goal.
don't score robots, you score areas of the field.
Yeah, but we find the scores by the areas, but in the match we give any robots a score.
So what about when there is a situation where the roles change? You know, it happens a lot where defenders switch places with attackers, or there is a robot taken out and another enters in with another
The
ID.
score is changed, and based on the direction and the velocity.
So you dump the previous values and assign new ones?
Just a weighted amount of the previous value, just.
Okay.
Any other questions?
What is the 5-micron accuracy comes for?
Sorry.
What is the 5-micron accuracy comes for? Which part have that accuracy in the manufacturing? You said you have the accuracy of 5 microns in your design of.
Oh, sorry, I said 5 microns?
Yeah.
I meant 0.5 millimeters.
In which part?
In the stance.
The distance between the center of the wheel?
No, not actually. Suppose we want to have a vertical stance on the chassis, and if these, it goes like this or this, one of the wheel goes on the air.
How much?
0.5
Is that
millimeters.
so important? Because when the robot is accelerating with this deaccelerating, the chassis will be like this. So that tolerance is not so important in
Yeah,
manufacturing.
but when we are in accelerating, the importance is between the rear wheels. So it's not affected. But if these two wheels, when you go straight, if these two wheels are not the same, as long as they are the same, nothing really bad happens. But when these two wheels are not the same, they are not in the same position, something bad happens.
They are not actually circle. the wheels are not actually circle. So when they rotate, they go up and down. So that tolerance in manufacturing is not so important.
Manufacturing is not so important.
No, the tolerance in manufacturing
Oh.
is not so important because the wheels are not completely circle. When they rotate, they will go up and down. So we cannot control the value of the.
Yeah, actually, I'm not an expert one in mechanic. I ask my mechanical guys to, share ideas. It's just what we saw in our tests.
Okay, so I'm sure MRL's wonderful mechanical team will continue these discussions, but thank you, MRL. We'll do our next team then.